Hello and welcome to this video. In this video I will present the amazing data structure called Merkle Trees. So Merkle tree is essentially a binary tree based on hash functions, and they have the very nice property that you can give very efficient proofs of membership, which means you can efficiently prove that one element is in the tree without revealing the entire tree. So in this video I will introduce Merkle trees. Stay tuned. The next amazing data structure that we will discuss can be seen as a generalization of this linked list that we just saw to actually binary tree. And this is known as the Merkle tree. So what is a Merkle tree? Well, we will see a pictorial description here. A Merkle tree is a binary tree where the data are essentially stored in the leaf values. And then each of these data entries is hashed. And once we receive this hash, then two hashes are essentially combined as the childs in a binary tree by computing a resulting hash value, which means essentially parent node carries the hash value of its children's. And this is then done recursively until we reach the top, and this is the root of the tree. So Merkle trees have very nice properties. And in fact, you can essentially show that some element is inside of this tree with relatively small proofs. So what does it mean? Well, it essentially means that if I want to show you that an element is in this tree, then I don't need to reveal the entire tree. Right? Revealing the entire tree, speaking space and time-wise, would require essentially all of n elements, basically all of them. And to check if there would be no ordering, that essentially one element is in the set, right? You would have to compare element by element until you essentially find the matching element, or you essentially realize, well, it's not part of the list. So instead, with this beautiful construction of a Merkle tree, what you will do is you reveal everything that is necessary in order to compute a verification path. So what is a verification path? Well, let's take a look at this example here. The element for which we would like to prove that is part of the tree. So what do we need to publish in order to compute the verification path? Well, as you can see, D is essentially the input to the hash function, right? That's the element that's the step that is computed first. On the other hand, you can see that the other element, the H1, is also marked red. So this is the element that is necessary in order to compute the parent node above. So the first element that we need to reveal is the element H1, because given the element D, we can compute H0, and with H0 and H1 we can compute the root H01. So now we already managed to cover the complete left part of the tree. The remaining element that we need to publish is the other element there, which is H23. Given H23 and H01, which we just computed from the elements before, we can actually compute the hash of both values and compare whether this hash corresponds to the root. And this in fact is the verification path. So in order to prove that the element D0 is part of the tree, the only elements we need to reveal are H1 and H23. So of course this is a short tree, it's not very deep, and it seems that the gain is not that large. However, if you look at large trees, you will find out that you only need logarithmic many elements to be published as the proof, and this is the space, and the computation time is also logarithmic, and therefore it's a very efficient proof system. So where are Merkle trees used? Well, in the cryptographic context, Merkle trees have many nice applications. For example, you can turn a one-time signature scheme into a many-time signature scheme using Merkle trees. In the setting of cryptocurrencies, Merkle trees will actually be used in order to store the transactions, as we will see in the corresponding video. So I hope you liked the video, in which I introduced the notion of Merkle trees, and I essentially explained how the verification path in general works. So if you liked the video, then I would be happy if you press a thumbs up, and I look forward to seeing you either here or in class again.